once we have defined inductive sets, we can also build on them and define, in fact, functions on such sets, and we can define these functions in an inductive way, following the structure of those sets that we define them on. And these inductive definitions of functions or recursive definitions of functions are always going to follow the same pattern that we have seen before. So we will have the domain of these functions is going to be a set that has been inductively defined starting from some basis a0, and we are going to define inductively a function f defined on A and taking value in whatever set C in the following way. First of all, you will have to introduce this sort of induction basis, and you will have to define what the value of this function is for all these basic elements that you started from. So whenever you defined A, you started from A0, so that's how you are going to start defining your function as well. You will first give it values for all these elements from the basis A0. And then the second thing you do when you define this inductive or recursive function is this induction step. You will say if A is in A and it was defined following the definition of A in terms of A1, AK, some other elements of A, then we are going to simply follow the same structure. We are going to define the function in A in terms of the function in A1 and in all of these other terms all the way to AK. So there is nothing really, more sophisticated than that in here. You have a recursive definition of a set, and then that means that this set is obtained through a number of combinations of some basic elements, and following the same structure you can also define a recursive function, and it's going to follow the same structure. You will have some values for the basis, and then you are going to follow the way the elements are being formed, and you define the function in the same way. One note here is that the function f is well defined. In fact, following these steps 1 and 2 and applying them repeatedly, you are going to get the value for each element a of a. And I want to give you a number of examples just to show you that this in fact is a pretty simple idea, and it builds naturally on the way we have defined recursive sets. And I'm going to give examples, in fact, for each example of a recursive set we had in the previous video. So here is the first example I want to give. On the function 3n that we have defined, this was the set of all natural numbers divisible by 3. I want to define a function on 3n taking values in natural numbers. And I can define it in the following way. First of all, remember that 3n was defined by saying 0 is an element in this set, and then if n is an element, then n plus 3 is also an element. So we are going to define the function in the same way. We are going to define the value for 0, and let's say we give it f of 0 to be equal to 2. There is no particular significance, just a random value I put in this example. And then I'm going to define n plus 3 in terms of f. So f of n plus 3, I'm going to define it in terms of f of n. And then, for example, it could be, f of n plus 2, for example. And that's it. That's the whole definition of our function. And because 3n was defined recursively, starting from 0 and then going from each n to n plus 3, then we have, using this strategy, a value defined for each element of 3 of n. So here is an example of how this would go. Obviously, if you want to calculate the value of f of 3, you realize that 3 was obtained in our recursive definition of set 3n was obtained by noting that it's 0 plus 3, and so we can apply our definition, condition number 2, and this is going to be f of 0 plus 2, and using condition 1, f of 0 is 2, so it's 2 plus 2, and that equals 4. We can also take f of 6, for example, and we can say, well, f of 6 is f of 3 plus 3, and using condition 2 in our definition, this is going to be f of 3 plus 2, and f of 3 we just calculated that it's equal to 4, so that's going to give us 4 plus 2 equals 6. So that's one possibility of recursive definition for a function. Here is so this was one example. I want to give you another example in here, and this is now going to build on our definition of all the words over a given alphabet sigma, and I want to introduce here the length function, the length of a word. And so we have sigma is the alphabet, obviously a finite alphabet as always, and the length of a word, so is going to be simply the number of letters in that word. And we can define this function, I'm going to put it in between two vertical bars, so that's like the module, but it's for words is going to be signifying the length of that word. So it's a function defined on sigma star, so it's going to have a value for each word over alphabet sigma, and it's going to have as values a natural number. And here is how we define it. First condition is, remember sigma star was defined in this way. First we said the empty word is in sigma star, and then we said if we have a letter and a word, then the concatenation of that letter and word gives you another word. So I'm going to define it using the same strategy. I define the length of the empty word to be 0. Obviously that's a natural definition because it consists of no letters. And then the other one was if W was obtained as concatenation of a letter A with a word U, so A in sigma, U in sigma star, then our function, the length of W, is going to be one more, so there is one letter, so one more than whatever U has. And again, the same pattern, we define the function on a longer input in terms of the function applied to a shorter input, following the structure of how this input was obtained. So for example, if you want to calculate the length of say word A, B, C, this is going to be, I'm just going to show where the concatenation is done. So this is letter A times word BC. So that applying, condition 2 in our definition is going to be 1 plus the length of BC. And that's 1 plus, and I'm just showing that this word is formed by letter B times word C. So that's again 1 plus the length of C, and we have another one in here. So it's going to be 2 plus the length of C. And then the word C is going to be letter C times the empty word. And so that's going to be 3 plus the length of the empty word. I just indicate again condition 2 here and condition 2 in here, and condition 1 comes in here. The length of epsilon is 0, so all in all that gives us 3, and intuitively that's exactly what we wanted to have. The length of this word consisting of 3 letters is exactly 3, but you can really trace this through repeated applications of these conditions 1 and 2. One more example in terms of words, and this is going to be useful also in some other occasions. It's about having a word and then defining what the word is if you read it right to left rather than reading it left to right as we usually do. And this is called the mirror image. So I want to define the function that's mirror image. So the mirror image, this is a function that takes value. I'm just going to I'm going to indicate it with the letter R, and that's going to be put somehow in the exponent. You will see in just a moment. So this function is going to be defined on sigma star, so it's applied to a word, and the result is going to be another word. And this is how we define it. Again, we have these two conditions, and the basis is going to be for the empty word. So the mirror image of the empty word is going to be the empty word. And so intuitively this makes sense. The empty word consists of no letter, so whether you read it from left to right or right to left, it's the same thing, it's still the empty word. And the second condition is going to be if W is equal to A times U, with A in sigma and U in sigma star, then the mirror image of W, so this is going to be defined as the mirror image of U times A. So this is again intuitively what you would like to have. You want to read right to left, so this is the same as reading first right to left U, so that's what I indicate here, the mirror image or the reverse image of U, and then at the end you put letter A. So for example, if you want to check what the mirror image of word ABC is, I'm just tracing the same example as I had here on the left side. So we first realize that word ABC is formed as the concatenation of letter A with the word BC, and so by condition 2, this is going to be equal to the mirror image of BC times A, and then we check and we realize that word BC is letter B times word C. And so again, by condition 2 in our definition, that's going to be the reverse image of word C times, or concatenated with letter B, and then we have still letter A from here. And then we realize that word C is just letter C times the empty word, and reverse image of that. And again, we apply the second condition, and that's going to be the mirror image of the empty word times C, and then we had still times B and A. I say times instead of concatenation, but hopefully this is not confusing. And then finally, by applying the first condition, the mirror image of the empty word is the empty word, so the result is simply C, B, A. And intuitively, that's exactly what you would hope to get with this definition. The reverse or the mirror image of ABC is CBA, and that's exactly what we got. And again, we got this through repeated applications of these conditions 1 and 2. One more example in here, and this time is going to be in terms of the arithmetic expressions. I want to define, define a function. I'm going to denote this function by hash, and this is going to be defined on a set of arithmetic expression over that alphabet of variables that we considered in the previous video. And this function, the purpose is to calculate the number of operators in a given arithmetic expression. So the result is going to be a natural number. And the way we define this is again in the same recursive way. Condition 1 is going to be if you have a variable, and then the number of operators in a variable is going to be obviously 0. There are no operators, it's just variables. So for all the variables in our set of variables x. And the second condition is going to be you trace now how you are forming arithmetic expressions, and there were essentially 3 different ways. And one way was that you are taking 2 other expressions, e and f, and you put plus between them and parentheses left and right. So the number of operators in such an arithmetic expression is going to be however many you had in e plus however many you had in f plus 1. And this plus 1 is supposed to show you that you do have one extra operator in here. So you have this plus here, and that's reflected into the plus 1, and however many there were in e and f, you're going to add them onto your expression. Then another way of getting an arithmetic expression was you were taking existing arithmetic expressions and you were combining them with multiplication, and you were putting left and right parentheses around them. And in this case, it's the same idea. You have a number of operators in E, plus you have a number of operators in F, and then you have plus 1. And again, this plus 1 is supposed to signify the fact that you have used this multiplication operator in building this arithmetic expression that you are now analyzing. And finally, the other way that we had for obtaining an arithmetic expression was you take an existing one and you put a minus in front and left and right parentheses, and in this case the number of operators is going to be however many you have in E plus 1, and again this plus 1 is supposed to show that you have used this extra unary operator in here. And the last example I want to give it something that I anticipated in the previous lecture. I want to define a function that's going to give you the height of a tree. And remember, I'm just going to show this in a visual way, just to remind you that we had this intuitive idea that you could have a number of combinations of your operators or labels, we call them, and your variables, and this could be shown in a graphical way. And the point of this height of the tree is to count how many levels you have in this tree, and so this would be level 0 that you start with, and this would be level 1, you go one level up, and this would be level 2. So the intuitive idea we would have in the case of this tree would be that the height should be equal to 2, because you go two levels up in describing the structure of this tree. So the definition is going to be, so I'm going to have H is defined on the set of trees, and is going to have as values natural numbers, and is defined in the following way. Again, we have these two conditions, and they mirror really the conditions we had when we defined inductively the set of trees. And the idea there was, if you have variables x and y, then the height is going to be, so the height of just applying it to variable x is going to be 0, and the height of y is 0. Remember that in our definition we only used two variables x and y. If you have more variables in your definition of trees, you would have to have more cases here in condition 1. And the second thing is that if your tree is of the form f of t1, t2, or t is of the form g of t1 and t2, with t1 and t2 trees, then here's how you are going to define the function. Let's think about this for just a moment. You have, so it's f, and then you have here this is 3 t1, and you have here these 3 t2, and they don't have to be of the same height. One could be maybe higher than the other one, just like we had, for example, in here in the one that we started with. On this tree is has a higher height than this tree. So you have this possibility in here, and the idea now is to define the height of this full tree in here. So what's the height of this full tree that we have? And so this is going to be defined like this. The height of 3t is going to be, now obviously 1 plus, and we have to see 1 plus what. And so it's something in terms of the height of t1 and the height of t2. And the one that has a higher height is going to contribute to the height of f. So this is going to be 1 plus maximum between the height of t1 and the height of t2. And I hope that this makes sense, especially by looking intuitively at this figure. I hope it makes sense that this is indeed the definition that you would like to have when you think about heights of trees. So once again, it's 1 plus. We certainly go one level higher, but then it depends which one of these is the tree with a larger height, and you take maximum out of those, and that's going to contribute to the height of the full tree that you are defining in here.